Beyond the orbit of Neptune right now, the orbits of icy worlds are tilting, not randomly, not chaotically, but all in the same direction, all by roughly the same angle, as if something is pulling on an invisible thread that runs through the entire outer edge of our solar system. No known planet sits in that region. No known force can produce what astronomers are measuring, and yet the tilt is there, persistent, clean, and growing harder to explain away. Before we dive deeper, if this kind of content genuinely interests you, consider subscribing, because what you're about to see only gets more surprising from here, and I post videos like this every single day. Now, let's continue. In August of 2025, a team at Princeton University published findings in the monthly notices of the Royal Astronomical Society that immediately shook the planetary science community. They had examined the orbital paths of more than 150 objects in the Kuiper Belt, the vast ring of icy debris that encircles the solar system beyond Neptune. What they found was not subtle. Beyond a certain distance from the Sun, the orbits of those objects were warped, tilted by about 15 degrees relative to the plane that the 8 known planets all share. 15 degrees does not sound like much in everyday terms, but on the scale of the outer solar system, it represents an enormous amount of energy, an amount that requires a gravitational source large enough to have been pulling steadily on countless objects for a very long time. The lead author of that paper was an astrophysicist named Amir Siraj at Princeton. He and his colleagues did not start from the assumption that a hidden planet was responsible. They started by trying to kill the idea entirely. For months, they tested every alternative they could construct. They checked whether a star that passed close to our solar system billions of years ago could have nudged those orbits into a tilt. It could not, at least not in any way that would persist. The math is straightforward. Any disturbance imposed by a stellar flyby would have been smoothed out by the gravitational influence of the giant planets long before now. Jupiter, Saturn, Uranus, and Neptune together act like a slow eraser, flattening anything that gets introduced from outside over millions of years. A stellar warp would be gone by now. They then tested whether the tilt was a scar left over from the formation of the solar system itself, a primordial feature baked into the disk before the planets were fully formed. That idea also collapsed. 4.5 billion years of gravitational evolution is more than enough time for any birth defect in the disk to be worked out. The solar system is an excellent ironing machine. It flattens and smooths its own fabric given enough time. The tilt they were observing had no right to still be there, which means something is keeping it alive. Something that is still out there today, still exerting a gravitational pull on the outer belt, still preventing the tilt from relaxing back to flat. Siraj put it plainly when describing his team's conclusion. They had needed a planet because without one, every mechanism they tested produced a warp that would have decayed. The warp is alive, therefore so is the source. The team gave the proposed object a name, Planet Y. To understand what Planet Y might actually be, start with its profile as derived from the orbital data. It is most likely larger than Mercury, but smaller than Earth. Its orbit probably sits somewhere between 100 and 200 times the distance between Earth and the Sun. That unit, the astronomical unit, is about 93 million miles. So Planet Y is between 9 billion and 18.5 billion miles from the Sun. Its orbit is tilted at least 10 degrees out of the plane shared by the other planets, and it has almost certainly been there for most of the solar system's history, slowly bending the trajectories of countless icy objects as it drifts through the dark on its enormous, lonely loop. Stop and consider that for a moment. A planet potentially larger than Mars, possibly with its own frozen surface, its own geological history, its own slow seasons measured in millennia, orbiting our own sun, and we have never seen it. Not in 400 years of telescopic observation, not in 7 decades of modern radio astronomy, not during decades of infrared sky surveys. Planet Y, if it exists, has hidden from us through 3 compounding factors: distance, size, and position. At 150 times the Earth-Sun distance, the sunlight reaching its surface is more than 20,000 times weaker than what we experience here. There is almost nothing to reflect back toward us. Even if its surface were bright white, a perfectly reflective snowfield, the signal would be vanishingly faint by the time it crossed that gulf. Its size makes the problem worse. A body smaller than Earth has a much smaller cross-section than Neptune or Uranus. Less area, less reflected light, dimmer signal. And its orbital tilt means it spends most of its time drifting through a part of the sky astronomers have historically ignored. Above and below the plane where all the known planets travel, in regions where nobody thought to look for a world of any significant size, Planet Y has been hiding above the deck this entire time. This distinguishes it sharply from the earlier hidden planet hypothesis known as Planet 9, which was proposed in 2016. That hypothesized object was supposed to be massive, somewhere between 5 and 10 times the mass of Earth, a super-Earth or a small Neptune. Planet Y is something more modest and in some ways more troubling, because modesty is what makes it invisible. A Mars-sized body on a tilted, distant orbit is almost perfectly designed by coincidence to evade every survey ever run. Small enough to be faint, far enough to move slowly, tilted enough to lie outside the search corridors that previous telescopes prioritized, and what Siraj was careful to emphasize is that Planet Y does not replace Planet 9. The two hypotheses are not competing with each other. They are explaining different anomalies. Planet 9, if real, would be responsible for the behavior of the most distant detached objects in the outer solar system, sitting 400 to 800 astronomical units from the Sun. Planet Y would be responsible for the warp in the moderately distant Kuiper Belt, between 80 and 200 astronomical units. Different distances, different masses, different gravitational effects. Both could exist simultaneously, two hidden worlds in the same dark backyard, each operating on a different layer of the debris field that wraps around our solar system. Before we follow the trail further outward, we need to understand the arena where all of this is happening, because the Kuiper Belt is not the simple frozen ring that early solar system models suggested. It is a layered, structured, deeply strange place, and understanding what it should look like is the only way to appreciate how wrong it currently appears. The Kuiper Belt begins just past Neptune's orbit at about 30 astronomical units and extends outward to roughly 50 astronomical units in its densest region. Beyond that, the structure becomes sparser, stranger, and far more difficult to interpret. The belt is not a solid ring, it is a swarm of icy bodies. Hundreds of thousands of objects larger than 60 miles across, each one drifting on its own orbital path around the Sun. Some carry frozen methane, some carry ammonia, some carry water ice older than the oldest rock on Earth. Pluto lives here. So does the dwarf planet Eris. So does a peculiar peanut-shaped world called Arrokoth, which the New Horizons spacecraft flew past in January of 2019, revealing a contact binary formed by the gentle collision of two smaller bodies billions of years ago. These are the leftovers of planetary construction. When the solar system was being assembled 4.5 billion years ago, not everything made it into a planet. Some material was scattered outward by the gravitational chaos of Jupiter and Saturn migrating through the early disk. Some was never incorporated at all. The Kuiper Belt is what remains, a frozen graveyard of raw material that never found a home. For most of the history of planetary science, the belt was considered quiet, finished, a place where ancient ice sat undisturbed in the dark, waiting for someone to find it. That assumption is now collapsing. The objects out here are not moving the way physics says they should, given only the known planets as gravitational influences. Some swing on orbits so elongated they look like comets, some are tilted sideways. Some appear to be entirely detached from the gravitational domain of any known planet. And the patterns in these abnormal orbits have been accumulating for years, growing more coherent and more difficult to explain as telescope technology improves. The 15-degree warp discovered by Siraj's team is the most recent and most statistically clean signal. But it is not the first strange thing astronomers found in the belt. Years before the warp was measured, there was something even more startling. A wall, a place where the Kuiper Belt simply stopped existing. Sail outward from Neptune. You pass 30 astronomical units, you pass 40, you pass 45. The density of icy bodies around you is roughly what models predict, perhaps slightly lower, but broadly consistent with a disk that extends gently outward. Then you reach 48 astronomical units, and the objects just stop. Not gradually, not as a smooth thinning, but abruptly. One side of that invisible boundary is populated. The other side is nearly empty. Astronomers call it the Kuiper Cliff, and the name is entirely appropriate because that is exactly what the data shows. A vertical drop in object density at a consistent distance from the Sun all the way around the solar system, the full orbital circumference. One cliff, one altitude, clean and uniform. This is deeply unexpected because early solar system models predicted the opposite. The disk of gas and dust from which the planets formed was supposed to extend outward for hundreds of astronomical units, thinning gradually but never cutting off sharply. If that model is correct, there should be more Kuiper Belt objects beyond 48 astronomical units, not fewer. The fact that fewer are there, far fewer, means something cleared the region. Something removed a large population of icy bodies from the outer disk and either scattered them to enormous distances, pushed them into the inner solar system where they became comets, or ejected them from the solar system entirely. Several explanations have been proposed. One is that the original protoplanetary disk simply ended at 48 astronomical units, that the solar system was born with a hard outer edge at that distance. But this only shifts the question. Why would the disk end there specifically? What physical mechanism draws such a clean line? Another proposal is that a passing star billions of years ago swept through the outer disk and scraped it away, leaving behind the sharp edge we observe. The problem with that idea is the same one that rules out the stellar flyby as the cause of the 15-degree warp. A passing star's gravitational effect would have decayed over time. The cliff would have softened. The edge would have blurred. Instead, it remains sharp. The most compelling explanation involves exactly the kind of object that Planet Y is hypothesized to be. One explanation for the Kuiper Cliff is that it arises as the consequence of resonance sculpting by a Mars-sized body sitting just outside the cliff area. A planet positioned just beyond 48 astronomical units, orbiting the Sun, pulling objects into gravitational resonances and flinging the rest outward, would naturally carve a clean edge into the belt. Objects inside a certain orbital distance get trapped or left in place. Objects beyond it get swept up, scattered, or ejected. The result is a cliff. What makes this particularly striking is that Siraj's team arrived at a similar mass estimate from an entirely different line of evidence. They analyzed the orbital warp. Older theorists analyzed the cliff. Different datasets, different analytical methods, similar answer. Something planetary is near the edge of the Kuiper Belt. The cliff and the warp may be two effects of the same hidden cause, but the cliff is not the only boundary in the outer solar system. It is not even the strangest one, because beyond the cliff, past the edge of the dense belt, in the empty wasteland where almost nothing should exist, astronomers have found objects on orbits so strange they should not be there at all. Objects whose trajectories no known planet can explain, that sit in the gravitational equivalent of no man's land, detached from everything. In 2003, a small team at Caltech pointed a telescope at the far edge of the solar system and found something that had no right to exist. A reddish, slow-moving dot smaller than Pluto, roughly 600 miles across, drifting through the dark at a distance of 86 astronomical units, almost 3 times farther from the Sun than Neptune. They named it Sedna, after the Inuit goddess of the cold sea, and when they calculated its full orbital path, they fell silent. The problem was its perihelion, the closest point of its orbit to the Sun. For most Kuiper Belt objects, the closest approach is somewhere between 30 and 40 astronomical units, close enough that Neptune can still tug on them, close enough that the giant ice planet can scatter them, trap them into resonances, or eject them into the inner solar system. Sedna's perihelion is 76 astronomical units. That number is shocking. It means Sedna never comes anywhere near Neptune. It cannot be a normal Kuiper Belt object that wandered out. Nothing we know of has enough gravitational reach to place a body on an orbit like this. And then there is Sedna's aphelion, its farthest point from the Sun, roughly 900 astronomical units. Its full orbital period is more than 10,000 years. This is not an object that casually wanders the outer solar system. It is a world that spends most of its existence in a darkness so profound that the Sun appears as little more than a particularly bright star. A single trip around the Sun takes longer than the entire span of recorded human history, multiplied several times over. By the time Sedna returns to its current position, the constellations will have shifted into arrangements that no human civilization has ever seen. How did it get there? No force from any known planet can explain Sedna's perihelion. The Sun's gravity alone would not strand a body that far out. To lift an object's closest approach to 76 astronomical units from its original position in the belt requires something external, a gravitational kick from a massive object that could reach out that far. 2 candidates have always dominated the discussion. A star that passed through the outer solar system billions of years ago during the crowded early period when the Sun was still embedded in its birth cluster, surrounded by thousands of other young stars drifting in close proximity. or a large hidden planet, sitting between Sedna's perihelion and aphelion, exerting a slow, steady pull on the object over billions of years. For over a decade, Sedna was the only known object on this kind of orbit. Astronomers wondered if it was a fluke. A single data point cannot establish a pattern. Then, in 2014, two astronomers named Chad Trujillo and Scott Shepard announced that they had spent 2 years quietly tracking a faint dot at the edge of the solar system. Its formal designation was 2012 VP113. Its informal name was Biden, coined during the Biden vice presidency. Its perihelion was about 80 astronomical units. Its full orbit stretched out for hundreds of astronomical units before curving back. A complete trip around the sun takes more than 4,000 years. Sedna was no longer alone. And the significance of two objects is not the number itself, but what the two objects had in common. Both were detached from Neptune's influence. Both had enormous orbits. And both had their orbits oriented in roughly the same direction in space. Their long axes pointed toward a similar region of the sky. Random gravitational scattering should spread orbits in all directions, like seeds thrown into the wind. Instead, these two pointed the same way. Trujillo and Shepard ran the numbers and concluded the alignment was not random. They proposed that an unseen planet beyond Neptune might be shepherding the most distant objects into matching orbits. This was the first formal suggestion of what would later become the Planet 9 hypothesis. Picture two compass needles lying on a table, both pointing toward the same direction. If you had placed them randomly, they would almost certainly have landed at different angles. But if there is a magnet beneath the table, and the needles are made of iron, they will align. The magnet is invisible, its effect is not. Sedna and its companion are two of those needles. Their alignment is the first evidence of an invisible hand. Over the following decade, more extreme objects were found in the outer solar system. Most of them remained controversial. The data was messy. Telescopes can only detect what is bright enough to catch, and most of these distant worlds reflect almost no light. Finding objects this far out, as astronomer Scott Shepard described it, is like trying to spot fireflies on the dark side of the moon. Small, slow, and nearly invisible. The handful of objects found in this region became known as sednoids, detached, distant, ancient. Then in 2023, a Japanese team using the Subaru telescope on top of Mauna Kea in Hawaii found a fourth sednoid. The project was called FOSSIL, an acronym for Formation of the Outer Solar System, an icy legacy. They were scanning the outermost edges of the solar system systematically, looking for exactly the kind of ancient, detached objects that could tell them something about the forces that shaped the early solar system. The new object was faint, moving at a glacial pace against the background stars. Confirming its orbit required months of tracking, then more months using the Canada-France-Hawaii telescope to nail down the details. By mid-2024, the orbit was confirmed. The object was real. It had a perihelion of about 66 astronomical units and a full orbit that stretched out to 252 astronomical units. They named it Ammonite, after the spiraled fossils of ancient sea creatures. Its formal designation was 2023 KQ-14. When the team overlaid Ammonite's orbit on a map of the other three sednoids, something was immediately wrong. Sedna, VP113, and a third sednoid called Leleaku Honua all had orbits that pointed roughly the same direction. Their alignment was the foundation of the Planet 9 hypothesis. Ammonite pointed the opposite way, whereas the orbits of the three previously known sednoids clustered between 0 and 90 degrees in their orbital orientation. Ammonite's orbit pointed toward 271 degrees. This is not a small disagreement. Ammonite was the mirror image of the other three. The implications were immediate. If you have three arrows on a table pointing east, and a single theory predicts why they point east, and then a fourth arrow appears pointing west, the theory has a problem. The team ran simulations asking whether a single Planet 9 in its originally predicted orbit could produce all four sednoids. The simulation said no. The researchers concluded that the existence of Ammonite lowers the likelihood of the Planet 9 hypothesis in its original form. More damaging still, the simulations showed that a Planet 9, sitting where it was originally predicted, would have ejected Ammonite from the solar system entirely. The fact that Ammonite is still here, on a stable orbit that numerical simulations show has been maintained for at least 4.5 billion years, means either Planet 9 does not exist, or it sits much farther out than originally proposed, perhaps at 1,000 to 1,500 astronomical units, where its influence is gentler and its reach longer but softer. This is the central tension that now runs through all hidden planet research. The evidence is real. The anomalies are real. The 15-degree warp is real. The Kuiper cliff is real. The aligned sednoids are real. The perpendicular orbits are real. All of these things are measured. But what exactly is causing them, and whether it is one object or two or three, and whether any of them are still in the solar system, remains genuinely unresolved. Ammonite did not kill the Planet 9 hypothesis. It complicated it. And the complication points to a possibility that is in some ways more unsettling than a single hidden planet. A planet that is no longer here. Consider the third scenario in the Planet 9 debate. Not that Planet 9 is far out and still present. Not that it never existed, but that it did exist and was later ejected. In the chaotic early history of the solar system, the giant planets were not in their current orbits. Jupiter and Saturn migrated significantly. Uranus and Neptune may have swapped positions. These migrations involved gravitational interactions, violent enough to scatter smaller bodies across enormous distances. They could also have ejected planets entirely. A body in the wrong orbit at the wrong time during one of Jupiter's gravitational surges could have been flung outward beyond escape velocity, launched into interstellar space. If that happened, the planet would be gone. But the orbits it had already perturbed would remain, frozen in place, ancient gravitational fingerprints that persist long after the sculptor has left. Ammonite's orbit, stable for 4.5 billion years, may be one of those fingerprints, set in motion during the first 100 million years of the solar system's history and then left alone when the architect was thrown out. The sednoids may be a family portrait of the early solar system, their configurations reflecting the forces that were active at the time of their creation, not the forces that are active today. Astronomers have already confirmed that rogue planets exist in large numbers throughout the galaxy, worlds without stars, drifting through interstellar space on journeys that may last longer than the current age of the universe. Estimates suggest there may be more rogue planets in the Milky Way than there are stars, trillions of orphaned worlds ejected from their home systems by gravitational encounters with siblings. If our own solar system ejected a planet, that planet would now be one of those drifters, cold and dark, carrying the chemical signature of a world formed around our sun, but no longer bound to it. The possibility that our family once had a ninth member, that we lost that member to the chaos of our own history, and that the sednoids are the orphaned records of what that member once did, is one of the more haunting scenarios in modern planetary science. But Planet 9 supporters have not abandoned the field. The strongest argument in their favor still holds up despite Ammonite. The original 6 aligned Kuiper Belt objects that Konstantin Batygin and Mike Brown identified in 2016 remain stubbornly aligned. The pattern has not gone away. Subsequent objects found in the outer solar system have on average leaned slightly toward the predicted cluster, though not as cleanly as the original 6. And when Batygin and Brown developed a method to quantify the observational biases of the telescopes that found those 6 objects, the alignment remained statistically significant even after correction. The probability that the original 6 aligned by random chance, even after accounting for telescope bias, is roughly 2 in 1,000. That is the kind of number that keeps a hypothesis alive. More persuasive still are the perpendicular objects. When Batygin and Brown built their original mathematical model of Planet 9's gravitational influence, they made a specific prediction. In addition to the cluster of aligned sednoids they were trying to explain, the model predicted a second population of objects that should also exist. Objects not aligned with the sednoids and not aligned with the planetary plane, but instead tilted to roughly 90 degrees, crossing the solar system's equator on paths that carry them far above and far below the plane of the planets. They predicted these objects would exist. Then they opened the existing catalogs and found them. 5 known objects fit this description precisely. 5 worlds on orbits that no other model adequately explains, all pointing in the direction the Planet 9 mathematics predicted. This is the most compelling kind of scientific evidence there is, not fitting a hypothesis to data that already exists, but making a prediction about data that has not yet been associated with the theory, and then finding that data already sitting in the catalogue. The perpendicular objects were never designed to support Planet 9. They pre-existed the hypothesis. Yet, when the math was done, they were exactly where the planet's gravity would have placed them. How does a distant planet create a perpendicular orbit? Through a long gravitational process involving the interplay of eccentricity and inclination. Over millions and then hundreds of millions of years, the gravitational influence of a tilted distant planet can slowly rotate the orbit of a smaller body in three-dimensional space, trading eccentricity for inclination and back again in a cycle called a Kozai resonance. The end result is an object whose orbital plane has been tilted nearly 90 degrees from where it started, swinging around the Sun above one pole and below the other in a path that looks entirely unlike anything produced by the normal flat disk of the solar system. These 5 objects should not exist. No normal solar system process creates them, but they are there, and they are where Planet 9's math says they should be. Before astronomers added hidden planets to their list of explanations, they had to carefully rule out the most obvious candidate for everything strange in the outer solar system: Neptune. Neptune is 17 times the mass of Earth. It sits at the inner edge of the Kuiper Belt at about 30 astronomical units. Its gravity reaches deep into the icy ring beyond it, scattering smaller objects, locking some into stable resonances and throwing others into wildly different paths. For decades, astronomers assumed Neptune could explain almost every strange feature of the Kuiper Belt. The tilts, the clusters, the detached objects. Surely a planet as massive as Neptune, sitting right at the doorstep, could account for all of it. It cannot. Neptune's gravitational reach has a hard mathematical limit. Gravity weakens with the square of distance. By the time you reach 50 astronomical units, Neptune's pull on a small object is roughly 1/3 of what it is at 30 astronomical units. By 100 astronomical units, it is 1/9. By 200 astronomical units, it is barely a whisper. Sedna's perihelion is 76 astronomical units. It never comes close enough for Neptune to touch it. Ammonite's perihelion is 66 astronomical units. Same story. These are exactly the objects that need explaining, and they are exactly the ones Neptune cannot reach. Siraj's team explicitly designed their analysis around this limitation. They filtered out every Kuiper Belt object that could plausibly be influenced by Neptune, and focused only on the population that was clearly beyond its reach. It was in that clean filtered sample, in the gravitational quiet zone, that the 15-degree warp appeared. This is one of the strongest logical arguments in the entire hidden planet debate. If Neptune cannot touch these objects, but their orbits are nevertheless warped, then something else is doing the touching. And since the warp is actively maintained today, that something has to be present today. Neptune also fails to explain the Kuiper cliff. The sharp edge at 48 astronomical units coincides approximately with a gravitational resonance Neptune creates at that distance. And Neptune does play a role in shaping the cliff's location, but Neptune cannot account for the severity of the emptiness beyond it. If the original protoplanetary disk extended far beyond 48 astronomical units, which models predict it did, Neptune's gravity would not have been powerful enough to clear all that material away. Something with more reach was needed, and Neptune certainly cannot explain the sednoids, whose perihelions are so far from the planet that Neptune would have needed to be roughly 100 times its actual mass to have influenced them. So the search has expanded beyond the known. If the 8 known planets cannot explain what is being observed in the outer solar system, the candidates have to include unknown objects. And some of those candidates are not conventional planets at all. One of the stranger proposals that emerged in discussions of the Planet 9 mystery is the idea of a captured rogue planet. Astronomers have long known that rogue planets are abundant throughout the galaxy. During the early years of our solar system, the Sun was still embedded in its birth cluster, a tight group of thousands of newly formed stars drifting in relatively close proximity. Gravitational interactions between stars in such a cluster are frequent. A rogue planet wandering through the cluster at exactly the right angle and speed could have been captured by our Sun's gravity, settling into a wide eccentric orbit far beyond Neptune. It would have brought with it the chemical composition of an entirely different stellar nursery, isotopic ratios of elements formed under conditions different from those that produced Earth or Jupiter. Battergen and Brown explored this capture scenario among several others for Planet 9's origin. A capture would explain why Planet 9's proposed orbit is eccentric and highly tilted, traits that are harder to produce for a planet that formed in the same flat disk as the others. A tilted distant orbit is easier to achieve through capture than through in-place formation. If this scenario is correct, and if the planet is ever found and studied up close, its surface chemistry could reveal that it formed around a different star. That it is, In a meaningful physical sense, an alien member of our solar system, Siraj's team noted the same possibility for Planet Y. The inclined orbit needed to produce the 15-degree warp is more naturally produced by a captured object than by one that formed within the original protoplanetary disk. Disks produce flat planets. Captured planets bring their own tilts with them. But a captured planet raises a deeper question. If our sun can acquire a planet from interstellar space, how confident are we that all 8 known planets formed here? The small, rocky inner worlds, the gas giants, the ice giants, we assume they all emerged together from the same primordial disk. That assumption has never been seriously challenged for the inner solar system, where the chemical and isotopic evidence is strong. But the outer solar system is a different environment with less evidence and more room for surprises. While the debates about Planet 9 and Planet Y continue in the published literature, the data situation is about to change dramatically. On a mountain in Chile, 8,800 feet above sea level, in the dry Atacama region where the air is so still that distant stars barely twinkle, a new observatory began operations in 2025. Its full name is the Vera C. Rubin Observatory, named for the American astronomer who first found conclusive evidence for dark matter in galaxies. Its mirror is more than 27 feet across. The camera attached to it weighs 3 tons and contains over 3 billion pixels. It is the largest digital camera ever built. Every exposure captures an area of sky larger than 40 full moons. The observatory's signature project is called the Legacy Survey of Space and Time, a 10-year sweep of the entire southern sky, photographed every few nights. In a single night, this telescope will image thousands of square degrees. Over 10 years, it will produce the most complete time-lapse map of the night sky in human history. For the search for hidden planets in the outer solar system, this telescope is everything. Current estimates suggest the Vera Rubin Observatory will discover between 20,000 and 40,000 new Kuiper Belt objects in its first few years of full operation. The total number of known trans-Neptunian objects will increase by a factor of 5 to 10 almost immediately. Every statistical question in the outer solar system becomes vastly more tractable when the sample size multiplies by that much. The 15-degree warp that Siraj's team identified using 150 objects will either become an overwhelming signal or dissolve into noise once 10 times as many objects are measured. Either outcome advances science more in a few years than decades of previous observation. The alignment of the sednoids that launched the Planet 9 hypothesis will be subject to the same test. The original 6 objects will be joined by hundreds more extreme trans-Neptunian objects. If most of them align in the way Planet 9 predicts, the statistical case becomes nearly airtight. If most of them do not align, or if their orientations distribute randomly, the hypothesis faces a serious reckoning. There is also a real possibility that the Vera Rubin Observatory will photograph one of these planets directly. Planet Y, if it exists at about 150 astronomical units with a diameter somewhere between Mercury and Earth, would shine at roughly magnitude 21 or 22 in visible light. That is well within the detection capabilities of the observatory's camera and software. Planet 9, being farther at 400 to 800 astronomical units and correspondingly dimmer, would be more challenging, but still within range at the brighter end of the predicted distance range. The telescope's software is already being developed to automate the detection. Every image taken will be compared to the previous image of the same patch of sky. Anything that moves will be flagged. A planet at 150 astronomical units would shift its position by a detectable amount every few weeks. A planet at 400 astronomical units would shift more slowly but measurably over months. This is exactly the kind of patient, systematic search that hidden planets require and that previous telescopes lacked the throughput to perform. Astronomers working in this field have described the coming decade as a golden age for outer solar system research. Mike Brown, the astronomer who discovered Sedna, who later helped propose Planet 9, and who also led the reclassification of Pluto as a dwarf planet, has said publicly that he expects either confirmation or definitive rejection of the Planet 9 hypothesis within 10 years of the Vera Rubin Observatory's full operation. The wait, in other words, is almost over. While visible light surveys from the ground prepare to transform the field, another search strategy is already producing candidates. It exploits a physical fact that no distant planet can escape. Everything with a temperature above absolute zero emits infrared radiation, heat. A planet at 150 or 400 astronomical units would be extraordinarily cold, perhaps negative 370 degrees Fahrenheit, or colder. But cold is not the same as zero. Even the most frigid world in the solar system would glow faintly in the far infrared. And in the infrared, the background sky is much darker than invisible light, making cold objects easier to pick out against the darkness. In 2025, a team led by Amos Chen at National Tsinghua University in Taiwan published a striking result. They had combined archived data from the Akari Space Telescope, a Japanese infrared mission that surveyed the sky between 2006 and 2007, with even older survey data from the Eris satellite operated in 1983. 23 years separated the two sets of observations. That gap is large enough that a planet at 400 astronomical units would have shifted its position in the sky by a measurable amount between the two surveys. Background galaxies would not move. Background stars would barely drift. A planet in our solar system would have moved just enough to stand out. The team searched for objects that appeared in both surveys, but had shifted position by the expected amount for a Planet 9-sized body. They found two candidates. Both sat in the region of sky where Planet 9 should be. Based on the orbital predictions derived from the sednoid alignment, both had the right brightness for a body 5 to 10 times the mass of Earth at the predicted distance. Both had the right amount of positional shift between the two survey epochs. This is not yet a discovery. The Akari and Eris data is decades old and limited in resolution. Cosmic rays can mimic the appearance of faint stationary objects. Background galaxies can flicker. Asteroid belt objects moving at the wrong rate can create false positives. The candidates need to be confirmed in modern telescope data, and multiple teams around the world are currently working on exactly that. Results could emerge within 1 to 2 years. If even one of the candidates survives scrutiny and is confirmed as a real planet, it would be the first new planet discovered in our solar system since Neptune was found in 1846. A world with a surface that could be photographed in detail, a gravity field that could be mapped, an atmosphere if it has one that could be analyzed, a target large enough to eventually send a spacecraft toward. Even the detection strategy itself carries a kind of poetic logic. The planet that has hidden from telescopes for centuries, evading observation by being too dark, too far, and too slow, may ultimately be revealed not by the light it fails to reflect, but by the heat it cannot suppress. Its own residual warmth from formation, leaking out into the cold at wavelengths that betray its presence to a sufficiently sensitive detector. The darkness that has concealed it is not absolute. Every cold thing eventually whispers. Among the discoveries that have come in parallel with the warp and the sednoid debate is one that adds a new layer of structure to the Kuiper Belt itself. In 2011, researchers identified a cluster of 189 objects near 44 astronomical units, all orbiting the Sun in roughly the same way, packed into a relatively small region of orbital space within the larger belt. They called it the kernel of the Kuiper Belt, a tight grouping that hinted something had organized this part of the belt long ago. Perhaps a planet drifting through and shepherding objects into a stable resonance. Perhaps a feature preserved from the original formation of the solar system. Then in 2025, the picture sharpened. Researchers at Princeton, working through the same team that produced the 15-degree warp analysis, announced something new. By running orbital data from 1,650 Kuiper Belt objects through a clustering algorithm, they had identified a second, more compact cluster sitting just inside the first one at roughly 43 astronomical units, an inner kernel inside the original kernel. This kind of layered substructure is not what a simple solar system produces. A simple solar system has a flat, smooth disk that thins gradually. Our solar system instead has bumps, clumps, layers of organized material at specific distances, separated by gaps where almost no objects exist. Each of these features is a record of something that happened to the belt over the course of its 4.5 billion year history. The inner kernel's discovery matters for the Planet Y search. Because if Planet Y is operating at 100 to 200 astronomical units, its gravitational influence should reach inward and affect objects in regions like the kernel zone. The Vera Rubin Observatory will generate far more data on this region than any previous survey, potentially revealing whether the substructure is consistent with a hidden planet's gravitational fingerprint or inconsistent with it. The Kuiper Belt is not a graveyard. It is a record. Every cluster, every cliff, every detached sednoid, Every perpendicular orbit is a line in a story that has been writing itself for 4.5 billion years. We are only just learning to read it. Now consider what it means if two hidden planets exist simultaneously. Planet Y at 100 to 200 astronomical units, modest in size, actively maintaining the 15-degree warp. Planet 9 at 400 to 800 astronomical units, larger, responsible for the aligned sednoids and the perpendicular orbits. Two separate gravitational presences operating on two separate layers of the outer solar system. Their existence would fundamentally change the picture of how the solar system is structured. We have spent centuries thinking of the solar system as consisting of 8 major planets, a belt of asteroids, the Kuiper Belt, and then nothing significant until the Oort cloud at thousands to tens of thousands of astronomical units. That picture is now genuinely uncertain, not because astronomers have made errors, but because the instruments and methods available before the last decade simply were not sensitive enough to reveal what the data was hiding. The outer solar system is vaster and more populated than our textbooks suggest. The number of significant gravitational objects it contains may be higher than we currently count. Some researchers have proposed that additional worlds could exist even farther out, sculpting populations of objects that we have not yet catalogued at all. The Oort cloud, a vast spherical halo of icy bodies extending from a few thousand to perhaps 100,000 astronomical units, is barely understood. It has never been directly observed. We infer its existence from the comets that occasionally fall inward toward the Sun on their long trajectories. If hidden planets can exist at 400 to 800 astronomical units, there is no physical reason why additional bodies could not exist at even greater distances, shaping the inner edge of the Oort cloud in ways we have not yet detected. The process of discovering these worlds, if they exist, will also tell us something fundamental about how planetary systems form in general. The outer reaches of a planetary system, the cold, dark regions beyond the snowline where ices are stable, are some of the least well understood environments in stellar astrophysics. Planets in wide orbits are extraordinarily difficult to detect around other stars. The two primary methods used to find exoplanets, the transit method and the radial velocity method, are both strongly biased toward close-in planets. The transit method works by detecting the tiny dimming that occurs when a planet passes in front of its star. A planet at 100 astronomical units orbits so slowly that it might transit its star once in thousands of years. The radial velocity method works by detecting the wobble a planet's gravity induces in its host star. At hundreds of astronomical units, a planet's gravitational tug on its star is negligible. These methods are effectively blind to the kind of planet that Planet 9 or Planet Y might be. As of 2026, more than 5,000 exoplanets have been confirmed. Many of them are unusual, hot Jupiters orbiting closer to their stars than Mercury orbits the Sun, super-Earths with no solar system analogue, planets on orbits so elongated that they experience temperature swings of thousands of degrees over a single year. But this catalogue, despite its size, reflects the observational bias toward the inner regions of other planetary systems. The outer regions of those systems are dark and largely invisible to current technology. We have catalogued the nearest trees in thousands of forests without being able to see what lies deeper in any of them. If hidden planets in wide orbits are confirmed in our own solar system, it would justify a fundamental rethinking of how common such objects are around other stars. It would motivate the development of new observational technologies specifically designed to search the outer regions of nearby star systems. Direct imaging missions using coronagraphs or starshades to block the light of a host star while detecting the reflected light or thermal emission of distant orbiting companions are already under development. A confirmed discovery of Planet 9 or Planet Y would immediately justify prioritizing such missions and targeting the outer zones of the nearest stars. The implications extend to the question of habitable environments beyond the obvious. Most discussions of habitability focus on the so-called habitable zone, the narrow band of distance from a star where liquid water can theoretically exist on a planet's surface. This zone is typically close to the star, but hidden planets in the outer regions of planetary systems could host moons warmed not by sunlight, but by the tidal flexing of their planet's gravity, or by radiogenic heating from the decay of radioactive elements in their interiors. Our own solar system already provides proof of concept. Europa, a moon of Jupiter, has a liquid water ocean beneath its icy crust. Enceladus, a moon of Saturn, actively shoots geysers of water vapor and organic compounds into space. Titan, also orbiting Saturn, has lakes of liquid methane and an atmosphere thick enough to obscure its surface. None of these worlds sits in the conventional habitable zone. All of them have conditions that might support some form of chemistry complex enough to be interesting. If similar moons exist around undiscovered planets in the outer regions of other star systems, the population of potentially interesting environments in the galaxy is much larger than current estimates suggest. The discovery of Planet 9 or Planet Y would not directly tell us anything about life, but it would force an expansion of the concept of where in a planetary system interesting things might be happening. There is also the question of what a discovery like this does to our sense of how well we understand our own neighborhood. 400 years have passed since Galileo first turned a telescope on the moon. In those 4 centuries, humans have mapped the planets, identified their moons, measured their atmospheres, landed on several of them, and sent spacecraft to the edges of the heliosphere. The Voyager probes, launched in 1977, have now crossed into interstellar space. We thought we had a comprehensive picture of our solar system. The outer solar system anomalies suggest we do not. A hidden planet would not just add a name to a list, it would demonstrate that the solar system we have lived in for the entirety of human history contains entire worlds that we have never detected, never photographed, and never studied. That these worlds may have been part of our gravitational family since the beginning, sharing the sun's pull for 4.5 billion years, waiting silently at distances we had systematically underestimated, is a reminder that familiarity is not the same as understanding. The Voyager spacecraft provide a useful reference point. Voyager 1, now in interstellar space, is approximately 24 astronomical units from the Sun as of early 2026. Planet Y is proposed to orbit somewhere between 100 and 200 astronomical units. Even our most distant man-made object has not reached the region where the smaller hidden planet might orbit. Planet 9, if it exists at 400 to 800 astronomical units, is between 17 and 33 times farther away than anything we have ever sent there. Any probe designed to visit these objects would need entirely new propulsion technology or mission timelines measured in decades. The Voyager probes took 45 years to reach interstellar space. A probe aimed at Planet 9 at even its closest predicted distance would take far longer using current technology, but the scientific return would be proportionate to the effort. A flyby of an undiscovered planet in the outer solar system would tell us more per mission dollar about the structure of planetary systems than almost any other space mission in history. The chemical composition of its surface, the shape of its magnetic field, if it has one, the structure of its interior inferred from gravity measurements, all of this would be new information about a class of object we have never encountered up close. Within the next few years, the Vera Rubin Observatory will have collected enough data to either confirm or challenge every major hypothesis currently competing in the outer solar system debate. The 15-degree warp will be measured against a sample 10 times larger than what Siraj's team had. The sedenoid alignment will be tested against hundreds of new extreme trans-Neptunian objects. The candidates identified in the infrared survey may be confirmed or dismissed by modern telescope follow-up. The inner kernel and the original kernel will be mapped in detail, revealing whether their substructure is consistent with a planet at 100 to 200 astronomical units. What scientists still do not know is whether any of these anomalies ultimately requires a planet, or whether some combination of mechanisms we have not fully modeled. The effects of stellar flybys during the sun's birth, the collective self-gravity of undetected small bodies, resonances with the known giant planets operating over long timescales, could account for the observations without invoking something new and large and unseen. The history of astronomy contains precedents for both outcomes. Planet Vulcan, hypothesized in the 19th century to explain a tiny anomaly in Mercury's orbit, turned out not to exist. The explanation was general relativity, not a new planet. But Neptune itself was discovered in 1846 precisely because 2 astronomers calculated where it had to be, from the anomalies it was inducing in Uranus's orbit. Predicting a planet from orbital anomalies and then finding it in the predicted location is one of the most elegant successes in the history of physics. The outer solar system is where one of those 2 scenarios will play out over the next decade. Either a new planet will be found and the history books will need rewriting, or the anomalies will dissolve under better data and the explanation will turn out to be something more subtle. Both outcomes are scientifically valuable. Science does not only advance when predictions are confirmed, it also advances when carefully constructed hypotheses are tested to destruction and the failure forces the development of better models. But the weight of the current evidence leans in a particular direction. The warp is real. The cliff is real. The sednoids are real. The perpendicular orbits are real. The infrared candidates are real, pending confirmation. The inner kernel is real. Each of these anomalies has been independently measured by different teams using different instruments in different parts of the sky. They all point toward disturbances in the outer solar system that the known 8 planets cannot explain. 2 independent lines of evidence, the sednoid alignment in 2016 and the orbital warp in 2025, using completely different methods and different populations of objects. Both arrive at the conclusion that hidden planetary mass exists beyond Neptune. The probability that all of this is coincidence is not 0, but it is small. And it is getting smaller every year as the catalogue of measured objects grows and the patterns persist. The sun has been burning for 4.5 billion years. Humans have been watching it with instruments for 400. The outermost reaches of its gravitational domain have been studied seriously for perhaps 30 years. In that context, finding that we missed 1 or 2 planets in our own solar system is not a failure of science. It is exactly what science looks like when it is working. The instruments improve, the data accumulates, the patterns become clearer, and eventually, the thing that was always there but too faint and too slow and too far away to detect becomes visible. At this moment, the icy worlds at the edge of our solar system are orbiting in patterns that do not match what the known planets predict. Something is pulling on them. The question of what that something is will be answered, almost certainly within this decade, by a telescope in Chile that has only recently opened its eye to the sky. If you find questions like this one compelling, the ones where science is happening right now, and the answer is not yet in, consider sharing this video and subscribing for more coverage of discoveries that are still in progress. The next decade in outer solar system research is going to be one of the most eventful in the history of planetary science. Whatever is out there in the dark beyond Neptune has been waiting a long time for us to find it. We are getting close. To fully grasp why the 15-degree warp is such a significant discovery, it helps to understand the concept of orbital inclination and why the solar system is flat in the first place. When the sun formed, roughly 4.5 billion years ago, it emerged from the collapse of a cloud of interstellar gas and dust. That cloud had angular momentum, a slow rotation inherited from turbulent motions in the surrounding galaxy. As the cloud collapsed under its own gravity, it spun faster, like a figure skater pulling in her arms. The cloud flattened into a rotating disk with the young sun at the center. That disk, called the protoplanetary disk or solar nebula, was where all the planets formed. Because they formed from the same flat rotating disk, the planets all ended up orbiting the sun in roughly the same plane. Earth's orbital plane defines the reference, called the ecliptic. Mercury is tilted about 7 degrees from this plane. Venus is slightly tilted, Mars by about 1.8 degrees. The giant planets stay within a few degrees of the ecliptic as well. The whole system is remarkably flat, a legacy of the physics that created it. Gravity is efficient. It wants things flat. It wants things to settle into their lowest energy configuration. And for a rotating system, that configuration is a disk. This is why any deviation from flatness in the outer solar system is physically informative. A tilt is not a default state. It is evidence that something imposed a force. When the Kuiper Belt objects beyond 80 astronomical units are found to be tilted 15 degrees out of the plane, the first scientific question is not whether the tilt is interesting. It obviously is. The first question is, what force could have created it, and why has it not relaxed away? The answer to the second part is the one that constrains the hypothesis so strongly. Gravity in the solar system is not a simple two-body interaction between the sun and each planet. Every massive object influences every other. The giant planets in particular, Jupiter, Saturn, Uranus, and Neptune, collectively exert gravitational torques on everything in the solar system. These torques act like slow corrective forces over millions and billions of years, nudging orbits back toward the plane, smoothing out any inclinations that are not maintained by an active gravitational source. This process is called secular evolution, and it operates on timescales that are long compared to human experience, but short compared to the age of the solar system. The key point is that a 15-degree tilt in a population of objects far beyond Neptune, if introduced by some one-time event in the past, should have been ironed out by secular forces long before now. The fact that it persists means it is not a relic. It is being sustained. There must be a gravitational source actively preventing the tilt from decaying, continuously refreshing the signal against the background tendency of the system to flatten itself. The size of the hypothesized object derives from this reasoning. The torque required to maintain a 15-degree warp in a population of objects spread across the region from 80 to 200 astronomical units against the combined flattening influence of the 4 giant planets puts a lower bound on the mass of the maintaining object. A body smaller than Mercury would not have enough gravitational reach. The object needs to be at least Mars-sized to do the job, and its orbit needs to be tilted itself, because a planet in the plane would not preferentially tilt objects upward. This is why the minimum 10-degree orbital inclination is built into the planet Y model. A planet sitting in the same plane as everything else would push objects toward the plane, not away from it. To produce an upward tilt in the Kuiper Belt, the perturbing planet must itself be tilted above the plane part of the time and below it on the other side of its orbit. The geometry of the observed warp is consistent with exactly this configuration. The region of sky where planet Y should be orbiting is now being scanned systematically. The Vera Rubin Observatory's survey area covers the entire southern sky, which includes most of the region where planet Y's inclined orbit would carry it above or below the ecliptic. Astronomers have also begun thinking about targeted searches using the James Webb Space Telescope's mid-infrared capabilities. At 150 astronomical units, even a Mars-sized body would have a faint but potentially detectable infrared signature with Webb's sensitivity if observing time can be secured for a targeted search of the right region. The challenge is that the search area, while narrowed by the orbital modeling, is still enormous by any practical standard. A tilted orbit at 100 to 200 astronomical units occupies a large arc of sky. Without a more precise constraint on the planet's current position within its orbit, the search requires scanning a large fraction of the sky at very high sensitivity. This is why the Vera Rubin Observatory's wide-field approach is better suited to the initial detection than a narrow-targeted instrument like Webb. The Vera Rubin Observatory sweeps the whole sky repeatedly and lets the planet reveal itself by moving between exposures, rather than requiring astronomers to guess where in its orbit it currently happens to be. Once a candidate is identified by the Vera Rubin Observatory's automated detection software, follow-up observations with large ground-based telescopes and with Webb could provide the astrometric precision needed to confirm the orbit. A planet at 150 astronomical units, tracked over a few months, would show enough curvature in its path to confirm whether it is on a bound orbit and to place initial constraints on its orbital elements. Those elements could then be compared directly to the predictions from Siraj's warp analysis to determine whether the object matches the expected profile. The prospect of finding planet Y within this decade is taken seriously by planetary scientists, not because the evidence is conclusive, but because the chain of reasoning is solid and the search tools are finally capable of testing it. A hypothesis that could not be falsified before the Vera Rubin Observatory began operating can now be falsified within years. That is progress. That is science, moving from the theoretical to the empirical. Let us also consider what the discovery would not tell us immediately. Finding planet Y would confirm its existence and allow measurement of its orbital parameters. It would allow estimation of its size from its brightness and distance, but it would not tell us its composition, its internal structure, its surface temperature profile, or whether it has any moons. These are questions that require either a long exposure spectroscopic observation with a large telescope, or ultimately a spacecraft mission. Spectroscopy from Earth-based or space-based telescopes at this distance would yield some information about surface composition, particularly if the planet has a reflective icy surface that carries spectral signatures of frozen methane, nitrogen, water, or carbon dioxide. But the signal would be extraordinarily faint and the observations challenging. A dedicated spacecraft mission to planet Y, if the planet is confirmed and its orbit is well determined, would be a generational scientific undertaking. The distance of 100 to 200 astronomical units puts it far beyond anything spacecraft have visited. New Horizons reached Pluto at 33 astronomical units in 2015 after a 9-year flight. It then continued to Arrokoth at 44 astronomical units by 2019. Getting to planet Y at 150 astronomical units would take proportionally longer with chemical propulsion, on the order of 20 to 30 years, depending on launch windows and gravitational assists. Getting to planet 9 at 400 to 800 astronomical units would be longer still. Decades of travel, possibly half a century or more. Nuclear thermal propulsion, which is a technology that has been under development for decades but never flown in space, could reduce these travel times significantly. So could solar sails for the early part of the journey or laser propulsion concepts. But none of these technologies are currently at the level of readiness required for a planetary mission. The next decades of space technology development will determine whether human-built spacecraft can visit the outer solar system's hidden planets within a reasonable time frame. What we do know is that the scientific community is paying serious attention. The discovery of the 15-degree warp, published in a peer-reviewed journal in 2025, generated immediate follow-up interest from planetary scientists in the United States, Europe, and Japan. The independent confirmation by Xiangyu Wang in Taiwan, who reviewed the hypothesis and found the simulations unable to remove the need for an actual planet, added credibility to the original paper. The infrared candidate search led by Amos Chen added a third independent line of inquiry pointing in the same direction. 3 different groups, 3 different methods, all converging on the same region of parameter space. A moderate mass planet at moderate distance with a tilted orbit. This convergence does not guarantee discovery, but it does reflect the systematic narrowing of the target that has characterized the most successful moments in the history of planetary astronomy. The discovery of Neptune itself followed exactly this pattern. Astronomers John Couch Adams in England and Urbain Leverrier in France independently calculated in the 1840s that the anomalies in Uranus's orbit required a massive body in a specific location beyond Uranus's orbit. They derived orbital parameters from purely mathematical analysis of the deviations in Uranus's measured path. Johann Galler at the Berlin Observatory pointed his telescope at the position Leverrier specified and found Neptune within the first hour of observation on the 23rd of September, 1846. The planet was found within 1 degree of the predicted position. This was one of the most celebrated moments in the history of science, a triumph of mathematical reasoning that revealed a new world through logic alone before any telescope had been pointed in the right direction. The Planet 9 and Planet Y searchers are attempting the same approach. Derive the existence and orbital parameters of an unseen body from the gravitational disturbances it imposes on visible objects. Point a telescope at the predicted location. The main difference is that the distances and detection difficulties involved are far greater than they were for the Neptune prediction. The orbital anomalies are also more complex, involving not a single well-studied planet like Uranus, but hundreds of small icy bodies distributed across a vast region with their own measurement uncertainties. The mathematical challenge is correspondingly harder, but the principle is the same. Gravity leaves marks. Follow the marks back to the source. The question of whether the warp, the cliff, the sednoids, and the perpendicular orbits all trace back to one source, 2 sources, or some other combination is genuinely open. What is no longer open is whether the outer solar system contains gravitational anomalies that the known 8 planets cannot explain. That question has been answered. They do. The follow-up question, the one that will define outer solar system astronomy for the next decade, is what exactly is responsible? One possibility that has gained some traction in the theoretical literature, though it remains less popular than the planet hypotheses, is that the outer solar system contains a population of small bodies distributed in a way that collectively exerts significant gravitational influence. Rather than one large planet doing all the work, perhaps many medium-sized bodies, too small to have been detected individually, collectively account for the anomalies. This idea runs into the problem that Battigan and Brown already tested and ruled out in their original 2016 paper. To account for the sednoid alignment through collective belt gravity, the belt would need to contain roughly 100 times more mass than it is observed to contain. The excess mass would also perturb Neptune's orbit in ways that would have been noticed decades ago. The collective belt hypothesis is effectively excluded. Another alternative that has been discussed involves the self-gravity of a distant disk of small bodies in the outer solar system, sometimes called the Mond scenario, or in some formulations, the Planet 9 substitute. In this framework, the distribution of mass in the outer solar system creates a collective gravitational potential that mimics the effects of a planet. The problem with this idea is similar. The amount of mass required, distributed in a way that produces the observed orbital clustering without also producing detectable effects on the inner planets, is not consistent with current mass estimates for the outer Kuiper Belt and Oort cloud. Modified Newtonian dynamics, sometimes abbreviated MOND, is a theoretical framework proposed to explain galaxy rotation curves without dark matter. It has occasionally been invoked as a possible explanation for the outer solar system anomalies as well, since the gravitational accelerations at hundreds of astronomical units from the Sun are extremely small, and MOND predicts deviations from Newtonian gravity in the regime of very small accelerations. However, MOND has been largely ruled out as a complete theory of gravity by other observations, and most planetary scientists regard it as an unlikely explanation for the Kuiper Belt anomalies, given that MOND's predicted effects at these distances are smaller than the observed anomalies. The dark matter hypothesis has also been invoked occasionally. The density of dark matter in the local region of the Milky Way is known from galactic dynamics, and it is not nearly high enough to produce gravitational effects on the scale of the solar system. Dark matter interacts with ordinary matter only through gravity, and its local density is far too low to perturb planetary orbits significantly. This explanation is firmly ruled out by the numbers, so the field keeps returning to planets, hidden, undetected, orbiting our own sun at distances we have not yet thoroughly searched. The evidence for their existence is indirect, but accumulating. The alternative explanations have been tested and found wanting, one by one. The search instruments are now reaching the sensitivity required to detect them directly if they are there. There is a broader lesson here about how knowledge advances in the sciences that depend on observation rather than controlled experiment. In physics, experiments conducted in a laboratory, a scientist can isolate variables, repeat tests, adjust conditions, and gradually narrow the uncertainty around a conclusion. In observational astronomy, the universe provides the data on its own schedule and in its own form, and the scientist's job is to extract signal from noise without being able to control what the signal looks like or when it arrives. This makes the process of confirmation fundamentally different. A hypothesis can be compelling, consistent with all available data, and derived from rigorous mathematics, and still remain unconfirmed for decades because the required observation has not yet been made. Planet 9 was proposed with strong statistical motivation in 2016. Nearly a decade later, it remains unconfirmed. Planet Y was proposed in 2025 with a different but equally serious statistical motivation. It is already being searched for by the most powerful survey telescope ever built. The gap between proposal and confirmation in observational astronomy can be long, but it has a hard limit set by the improvement of instruments. The Vera Rubin Observatory represents a qualitative leap in the relevant capability. If the planets are findable with current technology, the Vera Rubin Observatory will find them, or definitively constrain the parameter space within which they can exist. What happens scientifically if the search comes up empty? If the Vera Rubin Observatory runs for 5 years, discovers 40,000 new Kuiper Belt objects, and finds that the 15-degree warp disappears with the larger sample, and that the sednoid alignment dissolves into noise when hundreds of new objects are added, then the hidden planet hypotheses will be falsified. The anomalies that motivated them will be revealed as statistical artifacts of small samples, and the outer solar system will remain unexplained by additional planets, sending theorists back to the drawing board. That would be a genuinely interesting scientific outcome. It would not mean nothing is out there. It would mean the currently proposed objects in the currently proposed orbits do not exist in the currently proposed mass range. It would still leave open the possibility of smaller objects, objects in different orbital configurations, or objects even farther out than the current predictions assume. Science does not run out of questions. It runs towards sharper and sharper versions of them. But if the warp holds up with 40,000 objects, and if the sednoid alignment strengthens with hundreds of new extreme trans-Neptunian objects, and if the infrared candidates are confirmed in modern data, the conclusion becomes very difficult to escape. Something is out there, something large enough to bend the outer solar system, something that has been sharing our gravitational neighborhood for billions of years without our knowledge. the Sun has 8 known planets, or 9, or 10. Within this decade, we will know which of those statements is correct. Among the many compelling details of this story is one that has received less attention than it deserves. The researchers involved in this search are not working in isolation, chasing a fringe idea on the margins of planetary science. Amir Siraj at Princeton is a young astrophysicist who has published extensively on topics ranging from the properties of interstellar objects to the formation of the solar system. Konstantin Batygin and Mike Brown at Caltech have been among the most productive and rigorous planetary scientists of the past decade. Scott Shepard at the Carnegie Institution for Science has spent 2 decades conducting some of the most careful observational surveys of the outer solar system ever performed. These are not people prone to overclaiming. They are people who have built careers on precision and skepticism. The fact that researchers of this caliber, working independently with different data and different methods, keep arriving at the same conclusion, that the outer solar system contains at least 1 and possibly 2 significant undiscovered planets, reflects the genuine strength of the observational signal. It is not a consensus, because science requires more than convergent expert intuition. It requires direct observation. But the convergence of expert opinion, grounded in independent quantitative analysis, is what distinguishes a productive hypothesis from a speculative one. The next several years will determine whether this hypothesis is productive or ultimately wrong. The Vera Rubin Observatory will make the judgment. The data it produces will be made publicly available to the global astronomical community, allowing independent verification of every claim detection or non-detection. The process will be open, iterative, and self-correcting in exactly the way good science should be. And when the answer comes, whether it is a confirmed discovery or a definitive null result, it will tell us something important about our place in this solar system and about how honest we should be regarding the limits of what we think we know. The icy worlds at the edge of our solar system have been moving in patterns that do not match our predictions. They are slow, cold, and almost impossible to see. But gravity is patient, and its marks last for billions of years. We are reading those marks now, more carefully than ever before, with instruments powerful enough to read them clearly for the first time. The answer is close. The search has never been more focused, and the outer solar system, which seemed so settled and silent a generation ago, turns out to be one of the most interesting and unresolved places in our entire astronomical neighborhood. To put the scale of the Kuiper Belt in terms that feel real rather than abstract, consider a thought experiment. Suppose you could travel at the speed of light, the fastest speed permitted by physics, roughly 186,000 miles per second. At that speed, you could circle Earth about 7.5 times in a single second. You could travel from Earth to the Moon in a little over 1 second. You could reach the Sun from Earth in about 8 minutes and 20 seconds. You could reach Neptune, the outermost major planet, in about 4 hours and 10 minutes. Now, point your light speed journey towards Sedna at its current location, roughly 86 astronomical units. That trip takes about 11 hours and 58 minutes. To reach the outer edge of where planet Y is predicted to orbit at 200 astronomical units takes about 27 hours. To reach the inner edge of where planet 9 is predicted to orbit at 400 astronomical units takes about 55 hours. To reach the far end of planet 9's hypothesized orbit at 800 astronomical units takes 4.5 days, and even at 800 astronomical units, you would still be inside what astronomers consider the inner edge of the Oort cloud. The Oort cloud itself is thought to extend to perhaps 100,000 astronomical units. At the speed of light, reaching the outer edge of our gravitational neighborhood from Earth takes about a year and 4 months. The solar system, even defined conservatively by the extent of the Sun's gravitational influence, is almost incomprehensibly vast. Now consider that every argument in the hidden planet debate is happening at distances between 80 and 800 astronomical units, which is less than 1% of the full extent of the Sun's gravitational reach. We are talking about undiscovered planets in the inner backyard by the standards of the full solar system. And even this inner backyard has been, until very recently, almost completely unexplored in any systematic way. The reason is simple enough. At 80 astronomical units, even the largest telescope from the ground or from low Earth orbit sees objects that are extraordinarily faint. A Kuiper Belt object 100 miles across, roughly the lower limit of what we could call a significant icy body, would reflect so little light at that distance that detecting it requires several minutes of exposure time on an 8-meter class telescope. Survey science, which requires scanning large areas of sky quickly, has only recently reached the sensitivity needed to build a statistically meaningful catalogue of objects in this range. Before roughly 2015, the catalogue of known Kuiper Belt objects beyond 50 astronomical units was tiny, fewer than a dozen sednoids, a handful of extreme trans-Neptunian objects. The statistics were not sufficient to distinguish a real signal from noise. When Batygin and Brown published their Planet 9 paper in 2016, their statistical argument was compelling, but acknowledged to be preliminary. They were working with 6 objects in the critical population. 6 is not many. It is enough to see a pattern. It is not enough to be certain the pattern is real. Over the subsequent decade, the catalogue grew. By 2025, the population of known extreme trans-Neptunian objects had expanded enough that multiple independent groups could conduct their own analyses. Siraj's team had 150 objects to work with for the warp analysis. That is 25 times more than Batygin and Brown's original 6, though still a tiny fraction of what the Vera Rubin Observatory will eventually provide. The progression from 6 to 150 to tens of thousands reflects the standard pattern of observational science. A small sample hints at a pattern. A medium sample strengthens the signal and allows systematic error to be characterized. A large sample either confirms the pattern at high statistical significance or reveals it to be noise. We are currently in the transition from medium to large. The results of that transition will arrive within this decade. The pattern of how scientific understanding advances is also visible in the way the Sednoid story unfolded. Sedna was found in 2003. It was interesting but alone. One object cannot establish a pattern. VP113 arrived in 2014. 2 objects sharing a similar orbital orientation began to look like a pattern. Then the analysis of 6 aligned objects in 2016 generated the Planet 9 hypothesis. Then Ammonite arrived in 2023, pointing the other way, forcing reconsideration of whether the pattern was as clean as it appeared. Each new object added information. Each new piece of information constrained the space of possible explanations. This is not a story of scientists getting things wrong and then getting them right. It is a story of scientists updating a hypothesis as new data arrives, which is exactly how science is supposed to work. The initial 6-object alignment was genuine evidence for something unusual. Ammonite is genuine evidence that the original model was incomplete. The 15-degree warp is genuine evidence for something that the Sednoid alignment cannot account for by itself. Each anomaly independently constrains whatever is causing all of them. Consider the chain of reasoning about the warp specifically. A 15-degree tilt exists in the orbital planes of Kuiper Belt objects beyond 80 astronomical units. Tilt cannot be a statistical fluke in a sample of 150 objects at the 2 to 4% level. The tilt cannot be a relic of the solar system's formation, because secular dynamics would have erased it. The tilt cannot be a result of a stellar flyby because the flyby's effects would have decayed. The tilt requires an active gravitational source. The source must be outside Neptune's orbit because Neptune cannot impose a tilt at these distances. The source must be tilted itself to produce an upward warp, rather than a flattening effect. The size and orbital distance of the source are constrained by the spatial extent and magnitude of the warp. The constraints point to an object with a mass between Mercury and Earth, orbiting at 100 to 200 astronomical units, with an orbital inclination of at least 10 degrees. Each link in this chain is either a direct measurement or a mathematical derivation from established physics. There is no speculation involved in any individual step. The speculation, to the extent it exists, lies only in the claim that the chain correctly identifies the cause, an unknown systematic error in the orbital measurements, an unexplored physical process, some interaction between Kuiper Belt objects themselves that produces collective behavior not captured in current models. These are the places where the reasoning could be incomplete. The best response to this uncertainty is more data, which is what the Vera Rubin Observatory will provide. If the chain of reasoning is correct, more data will strengthen the signal. If there is a systematic error, more data of a different kind will reveal it. If there is an unexplored physical process, more data will produce anomalies in the signal that point toward it. The scientific method does not guarantee right answers on the first attempt. It guarantees that wrong answers become increasingly uncomfortable to maintain as data accumulates. One aspect of this story that deserves more attention is what it reveals. about the difficulty of completeness in astronomical surveys. Astronomers are accustomed to the idea that their catalogues are incomplete. The catalogues of galaxies are incomplete. The catalogues of stars are incomplete. The catalogues of exoplanets are dramatically incomplete. But the incompleteness of these catalogues is understood and characterized. We know roughly what fraction of galaxies, stars, and nearby planetary systems we are missing, and we correct for that incompleteness in our statistical analyses. The catalogue of outer solar system objects is incompleteness in a more problematic way. It is not only that many objects are too faint to have been detected, it is that the sensitivity of different surveys varies enormously across different parts of the sky, and that the orbit geometry of the target population makes some objects detectable only during specific windows when their orbits bring them close to the Sun, while objects on similar orbits with different phases are not detectable at all. This creates a complex observational bias that is difficult to characterize precisely without knowing the full population in advance, which is circular because characterizing the population is exactly what you are trying to do. Batterjin and Brown attempted to account for this bias in their revised statistical analysis. They modeled the sensitivity of each telescope that contributed to the catalogue and estimated what fraction of the putative Planet 9 aligned population would be detectable by those telescopes. Their conclusion was that even accounting for this bias, the alignment was statistically significant at the level of roughly 99.8% confidence. Critics disputed whether their bias model was complete. The debate has continued in the literature. The Vera Rubin Observatory will largely resolve this problem because its survey strategy is systematic, uniform, and well characterized from the start. The same telescope, the same camera, the same software, and the same sky coverage for every observation. The observational bias in the Vera Rubin Observatory catalogue will be far simpler to model than the combined bias of dozens of different telescopes with different sensitivities, different sky coverages, and different observing strategies. This is not a small improvement. It is the difference between trying to take a family portrait with 20 different smartphones held at different angles and different distances versus using a single professional camera on a tripod in controlled lighting. The Vera Rubin Observatory is the professional camera. It is worth reflecting on the specific geography of the anomalies. The Kuiper Cliff at 48 astronomical units, the orbital warp beginning at 80 astronomical units, the sednoids with perihelia beginning at 66 astronomical units and extending outward, the perpendicular orbits in the region beyond 50 astronomical units, the infrared candidates potentially at 400 to 800 astronomical units. These anomalies span an enormous range of distances. They are not all clustered at the same distance. They do not all point to the same location in the sky. This dispersal has led to the idea that what we are seeing might require multiple sources. Planet Y near 100 to 200 astronomical units, explaining the warp and possibly contributing to the Kuiper Cliff. Planet 9 at 400 to 800 astronomical units, explaining the sednoid alignment and the perpendicular orbits. And perhaps additional objects even farther out, sculpting the populations we have not yet discovered. The solar system may be more complex in its outer reaches than any model developed so far. If that turns out to be the case, the coming decade will reveal not a single dramatic discovery, but a sequence of revelations, each one requiring its own search strategy and its own confirmation process. The first planet to be found will change the question from whether any hidden planets exist to how many there are and where. The answer to the second question may take longer than the answer to the first. There is something intellectually satisfying about the fact that the outer solar system, the most remote and least explored region within our gravitational neighborhood, is now the frontier of planetary science. For most of the history of the discipline, the frontier was either the inner planets, where spacecraft could reach within months, or the giant planets, where the Voyager flybys in the 1970s and 80s provided the first close-up views. Pluto was the outer frontier of detailed exploration until New Horizons arrived there in 2015. Now the frontier has moved farther. The targets are not yet visible. The spacecraft that will visit them have not yet been built. The names by which they will eventually be known are not yet assigned. They may orbit our Sun at distances so enormous that the Sun itself appears as nothing more than the brightest star in an otherwise unfamiliar sky. They may have been there since the beginning, witnesses to the formation of every planet and every moon and every life-bearing world that came after. The fact that we have been their neighbors for 4.5 billion years without knowing they existed is not embarrassing. It is simply honest. The universe is large, our instruments have limits, and the outer solar system, even the portion within 1,000 astronomical units of the Sun, is genuinely dark. Finding what is there requires patience, systematic observation, and the willingness to follow the gravitational evidence wherever it leads. The evidence, right now, leads outward, past Neptune, past the Kuiper Belt's edge, into the tilted region where 150 measured orbits are all pointing slightly wrong in a way that has no explanation except the gravitational pull of something massive and hidden, something that has been pulling for billions of years, something that the next generation of telescopes is positioned, for the first time in history, to find. The question of what is out there has an answer. We simply have not measured it yet. What would it actually be like on the surface of Planet Y? If it exists, and if you could somehow stand on it? Imagination grounded in physics can take us there. At 150 times the Earth-Sun distance, the Sun is still in the sky. But it bears almost no resemblance to the Sun, you know. From Planet Y, the Sun would appear roughly 150 times smaller in diameter than it does from Earth. It would be a brilliant point of light, rather than a disk, the most luminous object in the sky by an enormous margin, but radiating far too little heat to warm anything significantly. The surface temperature on Planet Y would depend on its albedo, how much sunlight it reflects. A very bright, icy surface might reflect much of the already faint incoming radiation, keeping temperatures even lower. A darker surface might absorb more. In either case, the surface temperature would be somewhere in the range of -350 to -370 degrees Fahrenheit. That is close to absolute zero, though still above it. At these temperatures, most gases that we know as gases at Earth's surface are frozen solid. Nitrogen ice, methane ice, carbon dioxide ice. Even xenon and argon might be frozen to the surface. If Planet Y is large enough to have retained any atmosphere at all, it would be an extraordinarily thin one at these temperatures. Nitrogen, the main component of Earth's atmosphere, condenses into liquid at -320 degrees Fahrenheit and freezes solid even colder. At Planet Y surface temperatures, any nitrogen originally part of the planet's atmosphere would long since have frozen onto the surface. The same applies to methane and most other volatiles. If the planet has an atmosphere, it would be a trace of the most extreme cold-resistant gases, or it would be entirely absent. The sky, from that frozen surface, would be extraordinary. Without a significant atmosphere to scatter light, there would be no blue sky, no sunrise glow, no twilight. The sky would be black, the sun would be a piercing white point. The stars would be visible at all times, not just at night, because there is no atmospheric scattering to wash them out during the day. The Milky Way would arch overhead in full glory, its band of hundreds of billions of stars visible continuously, day and night, for the simple reason that there is no atmosphere to hide them. The other planets, including Earth, would not be visible to the naked eye from this distance. Jupiter and Saturn, the brightest planets in our sky after Venus, would appear as faint points if visible at all. The gravity on Planet Y's surface would depend on its mass and radius. If it is roughly the mass of Mars with a similar density, its surface gravity would be about 38% of Earth's surface gravity. You would weigh about a third of what you weigh on Earth. Objects would fall slowly. Walking would feel strange, each step launching you slightly too high before you settle back down. The experience would be similar in some ways to moving on the Moon, though the Moon's gravity is only about 17% of Earth's. The day length on Planet Y is completely unknown. It depends on its rotation rate, which would have been set initially by the angular momentum of the material from which it formed, and then modified over billions of years by tidal forces and collisions. Planets in the outer solar system tend to rotate relatively quickly, a consequence of the conservation of angular momentum during formation. Jupiter rotates in under 10 hours, Saturn in about 10.5 hours, Uranus in 17 hours, Neptune in 16 hours. Planet Y, if it formed similarly, might rotate in a similar time frame, but its surface would look the same at any hour. Black sky, blinding point sun, frozen landscape, stars overhead regardless of the local time. It would be one of the most alien environments that a human mind can coherently imagine while still being within our own solar system. Not another star system, not a distant galaxy. Our solar system, our sun overhead, our family of planets sharing the same gravitational parent, and yet entirely unlike any environment any human or any instrument has yet visited. The contemplation of what these outer worlds might be like is not mere philosophical musing. It shapes the scientific questions that guide the search and eventually the study of these objects. What composition would planet Y have? If it formed in the outer protoplanetary disk at its current distance, or was captured from elsewhere, its bulk composition would be dominated by ices with a rocky core below. This is the standard model for outer solar system bodies. A rock and metal core surrounded by a thick mantle of water ice, overlaid by a crust of more volatile ices like methane, nitrogen, and carbon monoxide. The proportions would depend on where in the disk the planet formed. Beyond the water ice line in the early solar system, at around a few astronomical units, water was the dominant solid. Beyond the carbon monoxide ice line, at much larger distances, carbon monoxide became abundant as a solid, a planet that formed beyond 100 astronomical units. If the disk extended that far, would have an ice composition different from Pluto's, richer in the most volatile ices, because the temperatures at formation would have been lower. These chemical differences could in principle be detected spectroscopically from Earth once the planet is found. The geological history of planet Y, if it has any, is constrained by its estimated size and distance from the Sun. A body smaller than Earth at these distances would have cooled rapidly after formation. The radiogenic heat from the decay of uranium, thorium, and potassium-40 would have powered some geological activity early on, potentially producing cryovolcanoes that erupted a mixture of water, ammonia, and methane rather than silicate lava. Pluto shows evidence of past geological activity of this kind. Its Tombaugh Regio, the heart-shaped feature revealed by New Horizons in 2015, is a nitrogen ice sheet within a large basin, likely maintained by convection in the nitrogen ice layer driven by residual internal heat. Planet Y, if somewhat larger than Pluto, might show even more geological complexity. Its internal heat budget would be larger. Its ice rock interior might have differentiated, with denser rocky material sinking toward the center and lighter ices rising. It might have had liquid water in its interior early in its history, a subsurface ocean, before the internal heat sources waned and everything froze. If any such ocean existed, it is long since frozen, at 150 astronomical units, with no tidal heating from nearby massive planets and only residual internal heat. The interior of planet Y would be as cold as its surface given enough time. These physical predictions are testable in principle with the right observations. Surface composition from spectroscopy, size and albedo from brightness measurements at known distance. Bulk density, and hence composition, from gravitational effects on any moons if they exist. Internal heat from thermal emission in the far infrared, a confirmed discovery of planet Y, would open a research program that could occupy planetary scientists for decades, extracting from a single discovery a wealth of information about the outer solar system's chemistry, dynamics, and history. The deeper context for all of this is that the solar system is still in the process of being understood. We sometimes speak of the planets as well-known objects, their properties measured and catalogued, their histories reconstructed, and for the inner solar system, this is broadly true. Earth, Mars, Venus, Mercury, the Moon. These are places where spacecraft have landed, where samples have been collected, where every major geologic feature has been imaged at high resolution. Jupiter and Saturn and their moons are known in substantial detail, revealed by the Voyager flybys, the Galileo orbiter, the Cassini mission, and numerous other spacecraft. Uranus and Neptune remain less studied, each having received only a single Voyager flyby, but their basic properties are well characterized. The outer solar system beyond 40 astronomical units is different. It has been mapped only at the coarsest level. Pluto was visited once. Arrokoth was imaged in a flyby that lasted hours before New Horizons receded on its way into the dark. Every other Kuiper Belt object has been observed only as a point of light in a telescope image. Their shapes, compositions, internal structures, and histories are largely inferred rather than measured. The existence of one or two hidden planets in the outer solar system is therefore not a departure from an otherwise complete picture. It is consistent with the broader reality that the outer solar system is a largely unknown place. We have barely scratched the surface of understanding what lies beyond Neptune. The Kuiper Belt itself was only confirmed observationally in 1992, when David Jewett and Jane Liu discovered its first object beyond Pluto. Before that, the existence of the belt was hypothetical, suggested by theorists but not confirmed. The entire modern era of Kuiper Belt astronomy is therefore only about 30 years old. In 30 years, we have gone from 0 known Kuiper Belt objects to thousands. We have discovered sednoids. We have found perpendicular orbits. We have identified a warp in the outer belt. We have mapped a cliff in the object density. We have found substructure within the belt. We have proposed 2 hidden planets. We are on the verge of launching the most powerful survey instrument ever aimed at this region. The pace of discovery has been extraordinary, and it is not slowing. What the next 30 years bring depends heavily on the next decade. If one or both hidden planets are confirmed, the outer solar system becomes a richly structured place with multiple large gravitational actors. Resources will flow toward characterizing these objects. Spacecraft mission proposals will proliferate. The community of researchers working in this field will grow. If the hidden planets are not found despite thorough searching, the outer solar system becomes a place full of unexplained anomalies, driving theoretical work to explain them in new ways. Either outcome generates more science than the current state of uncertain knowledge. The universe tends to reward the patient and the systematic. Anomalies that persist through increasingly thorough scrutiny tend to be real. The 15-degree warp has survived the most rigorous analysis its discoverers could devise. The sednoid alignment has survived a decade of additional observations, even if Ammonite complicated the picture. The perpendicular orbits are documented and well measured. The Kuiper cliff is undisputed. Something is out there. The solar system keeps leaving its marks everywhere we look in the outer belt. The source of those marks is yet to be seen, but the search is more focused than it has ever been, and the tools are more powerful than they have ever been. And the data is coming in quantities that will overwhelm the current uncertainties. Within years, the icy objects at the edge of our solar system have been silent, witnesses to 4.5 billion years of cosmic history. They remember the formation of the planets, the chaos of the early solar system, and whatever forces shape the orbits they now follow. They cannot speak, but they move, and the way they move tells a story. We are only now becoming fluent enough in the language of orbital mechanics to understand what that story says. The next chapter is being written right now, on mountaintops in Chile, Hawaii, and Japan, in data pipelines processing millions of images, in code running on supercomputers, fitting orbital solutions to objects so faint that they were invisible to every human who ever looked at the sky before the invention of the telescope. The answer is coming. The solar system has been keeping a secret, and it is about to run out of dark places to hide it. There is one more dimension to this story that connects it to the largest questions in modern astronomy: the nature of planetary systems in general, and whether our solar system is representative of what exists throughout the galaxy. In the past 30 years, the discovery of exoplanets has transformed our understanding of how planetary systems form and how diverse they can be. Before 1995, when Michel Mayor and Didier Queloz discovered the first exoplanet around a sun-like star, we had no direct evidence that planets existed anywhere beyond our own solar system. The assumption was that they did, but it was an assumption. Now, with more than 5,000 confirmed exoplanets and tens of thousands of candidates, it is clear that planets are ubiquitous. They form around most stars in an enormous variety of configurations. What is also clear from the exoplanet census is that our solar system is unusual in several ways. Most planetary systems discovered so far feature large planets very close to their stars. So-called hot Jupiters, gas giants orbiting within a fraction of an astronomical unit of their stars, are common in the exoplanet catalogue, yet our solar system has no such object. Jupiter, our largest planet, orbits at 5 astronomical units. Hot Jupiters are thought to form farther out in the disk, and then migrate inward through interactions with the disk gas or with other planets. Their prevalence around other stars suggests that planetary migration is common. Our solar system may have had hot Jupiter candidates early on that were prevented from migrating all the way in, or that were ejected before completing the migration. The absence of a super-Earth in our solar system is also statistically interesting. Planets with masses between 1 and 10 Earth masses, in orbits up to a few astronomical units, are the most common type of planet found around sun-like stars. Earth is at the low end of this mass range. Mars is well below it. There is nothing in our solar system in the super-Earth mass range in the inner system. This absence is real. and somewhat unusual compared to other planetary systems. These differences between our solar system and the average exoplanet system have been debated for years. One hypothesis is that Jupiter's early presence in the solar system prevented the formation or inward migration of super-Earths in the inner system. Another is that our solar system's configuration reflects a particular sequence of events during the nebular phase that is less common than the sequence leading to hot Jupiters and super-Earths. If Planet 9, or Planet E exists, the picture becomes more interesting. A hidden large planet in the outer solar system would move our solar system closer to the configurations seen in some exoplanet systems, where planets are distributed across a much wider range of orbital distances. In fact, some researchers have proposed that sub-Neptune planets in wide orbits, precisely the size range of Planet 9, may be more common around other stars than current data suggests. The difficulty of detecting them means the current exoplanet census severely underrepresents this population. A confirmed outer planet in our own solar system would provide a nearby test case for understanding this population. We could study it in far more detail than any exoplanet, measuring its orbit, composition, and physical properties through both remote sensing and potentially a spacecraft mission. What we learn about an outer solar system planet in our own neighborhood would directly inform our understanding of similar objects around other stars, even though those objects remain invisible to current instruments. The search for Planet Y and Planet 9 is therefore not just a local question about our own backyard. It is connected to fundamental questions about how often planetary systems include wide-orbit giants, how these objects form, whether they form in situ at large distances, or form closer in and migrate outward, and whether their presence or absence correlates with the architecture of the inner system. If our solar system has hidden planets at hundreds of astronomical units, other planetary systems almost certainly do too. The challenge of detecting them remotely around other stars is far greater than detecting them in our own system. But understanding them in our own system first gives us the physical intuition and the theoretical framework to look for them elsewhere. This cross-fertilization between inner solar system, knowledge, and exoplanet science has already been productive. The detailed study of Jupiter's atmosphere, magnetic field, and interior structure has informed models of gas giant exoplanets. The study of Pluto's geology and ice composition has informed models of icy bodies in the outer regions of other planetary systems. A study of a hypothetical Planet 9 or Planet Y would extend this contribution to the domain of cold, distant, sub-Neptunian planets in wide orbits. It would provide ground truth for a class of object that is currently understood only theoretically. Consider also what the discovery would mean for the history of the solar system. Every major addition to our understanding of the solar system's population has forced revisions to the models of how the solar system formed and evolved. The discovery that the asteroid belt contains bodies as large as Ceres, classified now as a dwarf planet, revealed that the asteroid belt was once more massive than it is today, most of its original material having been scattered away by Jupiter's gravity during the early history of the system. The discovery of the Kuiper Belt revealed that the region beyond Neptune was far more populated than models had predicted before 1992. The discovery of the Oort cloud was inferred from the trajectories of long-period comets and has shaped models of how the outer solar system interacted with the Sun's birth. A discovery of Planet 9 or Planet I would be another such revision. If Planet 9 is real at 400 to 800 astronomical units with 5 to 10 Earth masses, current models of planet formation struggle to explain how it got there. Planets of that mass do not form easily at such large distances from the Sun. The protoplanetary disk at those distances was too sparse to accumulate enough material in the time available before the disk dissipated. Planet 9 must have either formed closer to the Sun and been moved outward, or it was captured from another star system. Both scenarios require modifications to the standard model of solar system formation. If Planet Y is real at 100 to 200 astronomical units with a mass between Mercury and Earth, similar questions arise. Sub-Earth mass bodies can form at moderate distances and be scattered outward, but reaching 100 to 200 astronomical units through gravitational scattering during the late stages of planet formation requires a specific sequence of gravitational kicks that is statistically uncommon. Its tilted orbit adds another constraint. A tilted orbit at this distance is more consistent with capture or an unusually violent scattering event than with in situ formation, every additional constraint narrows the space of formation, scenarios that the models must account for. This is what drives progress in planetary formation theory. Not any single new observation, but the accumulation of constraints that rule out increasingly large portions of the parameter space, eventually leaving only the scenarios that actually happened. The outer solar system, with its strange cliffs and warps and detached worlds and perpendicular orbits, is providing more constraints per decade of observation than any other region of the solar system. It is the most productive frontier in modern planetary science, and it is about to become far more productive when the Vera Rubin Observatory reaches full operation and the catalogue of known objects multiplies by an order of magnitude. There is an emotional dimension to this search as well, though it is worth stating carefully to avoid overstatement. The idea that there might be another planet in our solar system, a world we share a sun with but have never seen, touches something fundamental about human curiosity. We have named our star. We have visited several of our sibling planets and sent probes to all of them. We have photographed the most distant reaches of the observable universe. But our own solar system, the place from which all of our astronomical observations originate, may still contain major undiscovered members. This is not a failure. Pluto was not discovered until 1930, 320 years after Galileo's first astronomical use of a telescope. The Kuiper Belt was confirmed only in 1992. The outer solar system is genuinely hard to survey. The timescales are long, the distances are enormous, the objects are faint. Finding things in the outer solar system takes decades of systematic effort, and the instruments capable of doing it efficiently have only recently become available. The discovery of a new planet, if it comes, will enter a lineage that includes some of the most celebrated moments in the history of astronomy. Uranus, discovered by William Herschel in 1781, using a telescope in his garden in Bath, England, the first planet discovered in the modern era. Neptune, predicted mathematically and then found at the predicted position in 1846. Pluto, discovered photographically by Clyde Tombaugh at the Lowell Observatory in 1930 after a systematic photographic survey of the sky. Eris, found in 2005 and large enough to force the reclassification of Pluto. Each of these discoveries changed the mental map of the solar system. Each one added something that was not expected, either in existence or in properties, and forced astronomers to update their models of how the solar system works and what it contains. A discovery of Planet 9 or Planet Y would be another such moment, another entry in that lineage, another reminder that the sky above us holds more than we have yet counted. The search continues tonight. The telescopes are open, the data is flowing, the algorithms are running. Somewhere in the black expanse beyond Neptune, beyond the frozen cliff of the Kuiper Belt's edge, in the tilted region where 150 measured orbits point slightly wrong, a world drifts through temperatures nearly at absolute zero, its gravity still bending the paths of countless smaller bodies. Still leaving its mark in the data, still waiting to be seen. We are watching. We are learning. We are almost ready to look in the right place, with the right instruments at the right sensitivity. The outer solar system's last major secret is about to run out of time to stay hidden.